Rn. Then the solution of that is the matrix we study, e to the it times e naught. So that's why we pay attention how to diagonalize or put this A in Jordan form so that we could do this calculation in an efficient way. And so we know that we can solve this, right? I don't think we are going to go back to this for the moment. So if A is diagonalizable, namely if there is a base EI such that EI, this is lambda I EI, then we can diagonalize it in this basis. The metric is just the metric A is just a diagonal with lambda 1 and so on. So we can partition this in blocks, and the solution will be, the solution of that will be some, use another name for that. E0 I EI e to the lambda I t, sum over I. So for this case we have to give one single number, a scalar. For this to have a solution we need to give some arbitrary vector, m vector. So this is a case we all love in physics because we can solve this problem. We can solve some other problems, for instance this, if this is the square root of y. The solution to that is, let me remember, I think is some constant times t squared. So if we take the right hand side, the left side, this will be 2at, and on the other side we have square root of a times t. We are taking the, say, the positive root. So we have a has to be 1/2, right? And this is 2 over square root of 2 of a. No. It's 2a over square root of a. So 2 square root of a has to be 1. So a has to be 4, a 1/4. So the solution is of this equation. This is solution that goes through 0, right? Because at t equal to 0 is 0. But notice that another solution of this equation is y equals to 0 directly, right? Because in both sides you get 0. So constant equal to 0 is a solution, and this also is a solution. So this equation has many solutions for the same initial data. And you stop at 0 and you have this solution, you have this solution, and you have many other solutions, because you can say you stop at some point, you have here t and y in this direction, and so you can have a solution that comes comes through the axis. Here at some point decided to go like t, like t squared, so it goes like this, or decide to go like here, or just stay here. All of these are possible solutions. Right? So these systems have many solutions. We are going to work with systems that have only a unique solution. So we will have to put some conditions here. And the condition that we need here is that this thing is not differentiable. It's continuous but not differentiable. We need some condition here that rules out these equations. And we are going to see that what we need is a Lipschitz condition, namely a condition, a function is Lipschitz if the following happens. When you do this, take any 2 points, nearby points, then this difference is less than some constant times x minus y. So a function satisfying this is Lipschitz. And if you have a function that is Lipschitz, we are going to use that when we prove existence, this condition, then you guarantee that the solution is unique. So from now on, we are going to ask our equations to be f such that they are Lipschitz. That's what we need. At least for first order equation, yeah. 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 So uniqueness requires Lipschitz. And to prove the way we are going to prove that the solution exists also needs a Lipschitz. We will see explicitly. Usually we just take differentiable, but the real condition is Lipschitz. I don't know whether you are familiar with this. For instance, the following function is Lipschitz. Let me remember how it is. It's x sine of 1 over x is Lipschitz near 0. But it's not differentiable, right? Because we have 1 over x. And why is Lipschitz? Because if you look at the plot, the graph of this function, it's a function that comes like that and starts going like that, but it's bounded by x. So it's Lipschitz, very straightforward. So we have f of x less equal to k times to x directly. So notice that here I put a norm, so we are thinking always we have a norm vector space. Huh? In a manifold you also have locally norms or distances, so you have this also. So on the final example we are going to see is this one here, dy dt is equals to y squared. So to find the solution of that, we just put the y's in one side and the dt in the other, and so on. We integrate this, and so we get 1 minus y this in some t0 and this in some t is equal to the integral of this side is t minus t0. So we can solve for y of t, right? We put this on the other side. So we change the sign, and then y of t is 1 over y of t0 minus t plus t0, or y0 y of t0 over 1 minus t minus t0 times y0 t0. So this is a solution. You give some value of y at t0 and you get this y. But notice the following. Suppose you take, say, t0 equal to 0, and you take y of t0 positive. Then say equal to 1. Say y of t0 equal to 1, t0 equal to 0, just to get one solution. And the solution y of t, in that case, is 1 over 1 minus t. So this solution goes to infinity for t equal to 1. Right? So look at this equation. This is as smooth as you can think of. So this equation does have no regularity problem, nothing, it's nice. Nevertheless, the solution exists for a finite time. Right? So when we do a theorem about the existence of ordinary differential equations, the only thing we can assert is that given some point we are going to find some interval where the solution exists. But we cannot prove in general that solution will exist for all time, because not true. This is a counterexample. So we are going to, in our theorem, we will only talk about some interval of existence. So the solutions can go bad, they can stop for some finite time. The only thing, and this is we are going to prove, is that the way this thing goes to infinity, to bad, is either the f ceases to be smooth at some point, or ceases to exist, or the y goes to infinity. That's the only two things that can happen. So when you are evolving, finding a solution, either you reach a point where the f does not exist, or you go to infinity. Those are the only possibilities. So the solution takes you in finite time to infinity. And this is what is going here. We go in finite time to infinity. Okay, because here this f is defined for all y's, no problem. So the only way the solution can stop existing is because at finite time we go to infinity. And this is what is going on here. So we have the examples. Now we are going to put our equations in a normal setting, in a standard setting, so that we can treat all of them in the same way. And this is the following. Suppose we have our equation. I don't like to use the red. Let's use x. I sometimes use x, sometimes I use y. We have our equation. So this was equation dy n minus 1 dt n minus 1 2 up to dy dt y. And before I put a t, I'm not going to put a t here. I will treat this problem first, and then I tell you how do we arrange this with the t. This is no problem. So we think about this ordinary differential equation. So we want to, this could be many things, so it's very hard to work with this in this way. So what we are going to do is to write an equivalent system which is on a vector, but it's first order. So the way we do this is to say, okay, I have a variable u1, which is y, and so dy dt, we are just writing the derivative of these things, is du1 dt, and now we are going to define another variable which is u2, which is this derivative, and so on. So I'm saying u2 is dy dt, and so on. u3 is dy, the second derivative, until you get to this point, right? un is dn minus 1 of y dt. And so, and this thing here then is just dun dt, right? Because it's a last derivative. So this we can write as f of un minus 1 until u1, right? And so you have the following system now. You take this as your equation, then un minus 1 to dt is so un minus 1, this was un minus now 1 is 2 derivative below, and this is the one before. So this is un minus 2, and up to un1 to dt, and then there's something wrong here. Un this should be u2, right? Yeah. This should be un. Okay. So you take this system. So now we have a vector u, which is u1, u2 up to un, and we have a system du dt is a big F of u. Let's change the name, u twiddle, and this F twiddle of u is just a vector that is F, the initial F, un up to u1, and here you have un up to u2. Okay? So the system is this one. So this is a first order system. And the claim is this system this we call 1, and this system 2, 1 is equivalent to 2. What does it mean, equivalent? That if I have a solution of system 1, then I have a solution of system 2. And if I have a solution of system 2, I have a solution of system 1, right? And how do I mean, this is more or less clear, but let me go. Suppose you have a solution of system 1, so you have a y of t. Yeah, that if you put it inside here, you get a solution to the equation 1. So then you write down the u1 this way. This is the definition of the vector u1. And you put it here. And from the definition, you know that these things are just part of the equation. So you satisfy almost everything here except the first component, and the first component is just equation, right? So you substitute here these things here, and you get the first equation. And if you have a solution of this, then you take the component the first component, u1, and start taking derivatives of all these components. These are the u2, etc., for instance, until you get up to the last one, right? You take all the derivatives of that, use the equation in every step, and you will get to this equation, right, for the last. The un to dt is this equation, right? And this coincides with the first element of this. So these two are equivalent. And this is the normal form of writing the equations. Because, why? Because these have a nice geometrical interpretation, so that we are going to see now. And once you know this geometrical interpretation, you understand most of ordinary differential equations. So the geometrical interpretation, you have an equation. Let me write just the y with the y now, dy dt. This is some f of y. And this y, so it's a first order equation, and this y belongs to some vector space that we can think to be Rn. And if we are in a manifold, say here, we can think of this as a set of coordinates. Say coordinates here in this manifold, in some patch. So you take a piece of the manifold, you express this patch with coordinates, so this is like Rn, R3 in this case, and this equation is there, is on these coordinates occur. So here what it means to have this equation, we say that a solution of that is a curve. So we have a curve from some interval to our piece of Rn. We have a curve like that. So a solution is this curve. So what this express, this is the following. If I have a curve, this derivative here is a tangent vector, it's the velocity vector of the curve. So it's something like this. Let's change color. At this point is this vector. So this is f. Right. So this equation tells you the velocity vector of my curve is this thing f. Okay? Nothing else. So an ordinary differential equation is a vector field. That's all. When somebody tells you I have this ordinary differential equation, you say, okay, this is a vector field. Show me the vector field. Right? So a vector field is an assignment of a vector to each point on a manifold or in a vector space. Huh? So I have vectors here. At every point I look, I have a vector. And what is a solution? Well, the solution is an integral curve. So if you take any point here, there will be a vector passing here. So I look for a curve such that when I move along the curve, I am always, the velocity vector coincides with the velocity vector of the field, with the vector field. Huh? So that's an ordinary differential equation. So this is a geometrical interpretation. An ODE is a vector field, a solution is an integral curve of a vector field. That means a curve which at each point in the curve, the velocity field coincides with the vector field. For instance, something you can very easily see is that if I have a point, any point, say with green, if I have a point here, and a vector field is defined here, then I will have a piece of curve going through this point. So to define one of these solutions, what I need is to say at some point where this curve crosses. So I say, okay, at T0, say this point here, this is T0. This point goes to here, and then I have a curve. Right? For instance, can it happen that I have a situation like this? Say in this point, I'm just not drawing. Okay, let me draw. A situation like this. I have a point, and I have a curve here, and I have another curve here. Can I have something like this? Well, in general, if the vector field is different from 0, no, right? Because at this point, either the vector field points in this direction or points in this direction, right? So I cannot have this because a vector field is unique. It's either this one or this one. But it could be that this point is 0. All right? So can I have a curve that crosses like this and crosses like this if the vector field here is 0? And the answer is no. We will have to work harder, but basically we are going to have uniqueness with this Lipschitz condition. So in this case, if the vector field is 0 here, there will be a solution which I will mark with some other color, say blue, a solution which is just staying in this point. Suppose this point is the point x0. So x0, x of t, or y of t equal to x0 is a solution. And since the solutions are unique, I cannot come like this and cross over this, because then the solution wouldn't be unique, because I will have this point with three solutions. The solution that comes this way and the solution that goes this way, and say these two also, right? So it cannot happen. So I cannot have something crossing. I can have a solution, y of t, y twiddle of t, that is approaching this point, but it takes a infinite time to get there. We will see an example. So these are the things we can have. A solution that comes to this point but never arrives, or leaves this point but never touches it. A solution that is here standing, and the same for this. But if the vector field is different from 0, the solutions are unique, because I cannot have this vector field pointing in two directions, right? So this is a very important consequence of this theorem. So basically, at every point, I have a unique solution. Right? Of course, as I say, I can have say an interval and a solution. Suppose, let me clean this. Say, given this point x0, I can have this solution, which comes with an interval. Here I have the R, and I can have another solution going through this point and this one, which has its own interval here. These two solutions are different in the way we define solutions. Yeah. So when we deal with uniqueness, we have to say in which sense the solution is unique. Because these two solutions go through this point at the same time, but they are different because the domain of definition is different. So we have to say what it means that the solution is the same, this uniqueness. Huh? And basically, just to say it, what is unique is the largest extension. If you extend the solution, we will see that we can extend the solution, then the maximal extended solution is unique. So you continue, if you continue the solution as much as you can, say up to here, and you continue the solution as much as you can up to here, and this solution with this interval is unique. Because we have all these problems. So this I mentioned because one have to get intuition of what an ordinary differential equation, what a solution is, what can I extend, not, etc. All very small problems which are very intuitive, and so it's good to discuss them. Any questions so far? Yeah. No, if you, so the solutions, the question is whether you have one or many solutions on how you call uniqueness. So the idea is you have a solution is a curve, And a curve is a map from some interval to my vector space. So it needs an interval and then the functional form. The algorithm to give me at every point a point here in the vector field at any time. So in this case, we can have two solutions, this green solution and this blue solution, and they are different. And this happens, it's not something that, for instance, you are in a manifold, say here, in a sphere, in R2, and you get some coordinate system that do not cover the whole sphere, so you get a solution in this coordinate system, and you get a solution in another coordinate system, and this coordinate overlap, and so you have points where the solution is in both coordinate system, and then you say, okay, I have a piece of a solution here, a solution, and I have another solution in the other chart, and I think of that as a unique extended solution. So what we do here is we say, okay, you have two solutions. So the case is, let me draw it. So maybe, if we are in manifold, say, to make more clear, we can have two charts here. So a chart, this is a chart of my manifold, a coordinate system exists here, and there is another chart here, say. And I'm looking for, let me draw it better. So we have the manifold here, and I have a chart here, and another chart here. So in this have a coordinate system, and here I solve the equations. I have a form for my equation, and I solve. And for this point, I find a solution. Let's do it in another color. I have a solution that starts, say, here, and comes here, covers the whole chart. And this is the point x0. So I have an interval here, and my curve, right? And here, I have another chart, another coordinate system, and I have a solution that comes from, say, to here, up to there. And so when I do the calculations, I only can compute this in, and I can compute this in two different charts. That's a real, when I do the calculation, I do that. And then I say, okay, these are different charts, but the manifold is unique. So this curve, I can extend it. And the way I extend is the following. I have say a y1 of t, which is the red one, and I have the blue one, and I say in the intersection, so I define a black one, y of t, the extension. The extension is y1 of t in the interval 1, and y1 of y2 of t in the interval . And why can I do that? Because I can prove that in the intersection, which is this region, they coincide. Because if they coincide at a point, they coincide in a neighborhood. So in the intersection, they coincide. So it's no problem in defining this. This is a unique solution. And this is the extended solution. And so now I continue this solution. If this finish here is either because my region where the vector field was defined ends, or I just continue. And this is a maximal extension. So it's extension the biggest extension I can do of my solution. That is, if I say, suppose this thing will continue here, the manifold with green. So suppose this, I have something like that. But just my method of computing solutions finished here. So I can stop at this point, right, and say, okay, this is a nice point, why not, and the vector field is defined, so I can continue my solution from here. Right? And this I can always do. That's what the theorem says. And we are going to see the theorem. So this way we create the maximal extension. And this maximal extension is unique. Or another way of saying this is, okay, if I have a solution y1 of t such that y1 of t0 is the point x0, and I have another one such that at this point and time is also x0, then there is a neighborhood where they coincide. Then y1 of t is equal to y2 of t in the intersection. That's the uniqueness, the local uniqueness. Okay, questions? So here I have a real physical example. This is a pendulum, the physical pendulum. So we have a pendulum with a mass, right? And in some other position, the position of the pendulum is given by theta. So the equation of the pendulum is d theta square dt, d theta is equals to, we can throw the constants away, and this is minus sine of theta. And this we can write as a first order system, saying, okay, B is, let's just write better. Defining d theta dB, that's the velocity, the angular velocity, this is v, and so this equation now becomes dv dt minus sine theta. So in this graph, this plot, theta equal to 0 is this point, this is theta, and this is v. So this coordinates theta, and this coordinates v. So this is the point where the pendulum is at rest, and this is a solution. The pendulum just stays there for all the time. This point here is the point where the pendulum is on the vertical. This is more than a pendulum, it's like a pencil. This point also is a solution. If you put the point, the pendulum vertical in the opposite direction, it will stay. But this point is unstable, right? As soon as you move it, it will fall. While this point is stable, as if you move it a bit, it will stay there. So we will see stability in a second. And the vector field is like that. So here it comes like that. So a solution will come this way. A solution will come this way because a vector field will go out here, will go out here. And here it will go around. So this is a solution, just going around. So these are the normal oscillations, right, like this. Then you start going with the amplitude, larger and larger amplitude until the pendulum goes vertical. You never get to the vertical. If you tick the pendulum so that it goes vertical, you put more force and more force, but the pendulum will take longer and longer to reach the upper part. And so at the end, there will be a limit where it takes infinite time to go there. So this curve finished before reaching this point, so it's never reached this point. It will take an infinite time to reach this point. And here you have oscillation. And if you pass the amplitude, then you can have, that is put more velocities, you can have a solution like that. And these are solutions that goes around the vertical axis. So here you have oscillations, but they cross the vertical axis, and here they have the other oscillations. Why this is? Virginia is doing something in my plot. Okay, I don't know why, but seems to be that people can write in my. That's nice. You can ask questions this way. Of course, this is the plot just extended, but the real manifold where this is defined is like this, right? It's a cylinder, right? Because the theta coordinate is periodic, so you should glue this point around, right? So this is a point A, say, here, and the point B is on the other side, and this thing here is the same as this thing here. After this line is periodic. So they are the same point. So this is a way to work. You have the pendulum size, so it's a second order equation. You know the highest derivative. This is the ordinary differential equation in the way it is presented to you, and you put it as a first order system. You look at the vector field here, right? The vector field, say for b equal to 0, this vector field is vertical. It's vertical. When b equal to 0, the vector has only vertical component. So it moves, say, like this, and here like that. When theta is equal to 0, it has only a horizontal component, so the vector field comes like this, and so on. So you can draw the vector field and guess what the solutions do without any computation. So let me talk about a bit conserved quantities, because sometimes conserved quantities appear, and in the codes sometimes you want to check your codes looking at the conserved quantities. So a conserved quantity is some function of y and it could be of t too, such that when you move it along a solution, this is 0. What it means is that you have the region where the vector field B is defined, which we call F. Let me call F. At every point. So you have the integral curves, which are your solutions, y of t. And you say that when you move along y of t, so you take c of y of t, and then take the derivative, total derivative. So here and here, this is equal to 0. And notice that this way I define it, I use the solution here, but I can write this as in a different way. I can write this as the derivative, the partial derivative with respect to t of c, that is, this is this derivative, the derivative with respect to t, plus the derivative of c with respect to yi times the derivative of yi with respect to t. But this, if I use equation, this is just the f. So this is, let me put the other way around. This is fi, this is this, times bc. So for instance, in the case that this doesn't depend explicitly on t, this is 0, and that tells me that the gradient of c has to be orthonormal. This is a covector. In the sense we study, this is a covector, and this is a vector, and it says that this contraction is 0. So the conserved quantities are functions defined here such that they are constants along the f. So for instance, if I have an f here that goes like this, a conserved quantity has to be something that is defined, is constant along this line. Right. So it has c equal to 1, say, is this. So when I move along, take the derivative of c along f, I get 0. Right? So these are conserved quantities. So how many conserved quantities, local conserved quantities, that I can define just in a region, I can have? Do you have any idea, somebody? Okay, let me construct for you some conserved quantities. What? Yeah, these are the globals, in some sense global. But I'm just thinking about without any structure. They are trivial, but they are nevertheless, according to the definition, they are conserved. So let me construct them. Suppose here you get some some coordinate system, which I'm going to take some surface here, which is n minus 1 dimensions, some surface sigma, and take a coordinate system here. So every point here you describe with n minus 1 points. So you have a coordinate x1 to x minus 1. There are coordinates here. And now for the xn coordinate, you say, okay, I take this to be transverse to the vector field f, so that the vector field always pinches the surface. And then I take as xn the coordinate that goes away from here along the curve. Right? I take I'm moving around this direction, I go through these curves. So I keep the other ones fixed. So this coordinate system now is constant. I take constant along this up to here. See? So I have a coordinate system. Right? So I have a here, a coordinate system here. This is x1, x2, and I keep going through this integral curve up to here. So I have a coordinate system like that. So I claim that all these are conserved quantities. Because if I take the derivative with respect to t, this is a derivative along this line, these quantities are constant, because I choose them. So locally there are many conserved quantities. Right? But in physics, what we are interested in is in the ones that come from symmetries, and they are global in general. For instance, let me give an example of some system that doesn't have any global conserved quantity. So suppose you have this space and your vector field here is like that. It's radial. So at every point is radial. So suppose you have a conserved quantity here. That means that the conserved quantity has to be constant along these integral curves. For instance, this one. So it has to be constant up to here. So this vector field goes to 0 in the middle, no problem. But I can approach the middle as soon as close as I want. So by continuity, if I move away from this point in this direction, this conserved quantity should have the same value. Okay? So the conserved quantity is, if here had the value 5, comes here, here, and it has to have the value 5, and also here. So the conserved quantity, the only conserved quantity is a constant, which is not very useful. While there are many conserved quantities locally, right? If I take some region here, I have many conserved quantities. I can have this 5, and I can have another one which comes like that, with different values, no problem. So this conserved quantity have different values here, but I cannot extend it globally. So since you can have local conserved quantities and global conserved quantities. And sometimes to check the code, you might need only a local conserved quantity. You don't need to have a global ones. Okay, let's make a break. Let's continue at 10:30. Okay, we continue now. So far, let me recall what we have so far. So far we have, we define first an ordinary differential equation of order f, n, and it was some the nth derivative equal to a function of all the previous derivatives in general. Yeah, I put a up to y, and then we took this system and convert into a big vectorial system of u. So we went to, from this system, say, suppose y was in R, now this thing here is in Rn. But what we gain this way is that we have a unique way of representing the equations, and we have a geometrical interpretation. This here is some vector field. So it's a vector at every point u in Rn. So at every point u, we have a vector, an arrow. And the solutions are integral curves along this, for instance, here. And so we have, just from the beginning, some geometrical interpretation. Also, we know that if the field is defined everywhere, this vector field, then at every point we have a solution going through this one, and this solution is unique. Right? So we can characterize the solution, say for instance, take a surface like that, take every point here, it will have a solution, and you have all the solutions given by points where this thing crosses this surface. Something like that we'll see later on. But given any point here, we have a solution going through this point. Of course, this is not unique. We can take any other surface and characterize the solution when they cross this surface here. And so this will be the same as the solution that we got here. But it's a way to classify the solutions. Now, what happens now if we add the time here? Well, what we can do is to get this system here and define a new hat, which is a vector that has the vector u and has the vector t, or let me call lambda. And you add to this system a new equation, which is d lambda dt equals to 1. With initial conditions, lambda t0 equals to t0. So now you have this bigger system. So this system and this system you collect into one. That is like that. That is f twiddle. And now f twiddle depends on u hat, right? Because we added the time. So here we have the u hat, and here you have 1. And this system is again of the same type in general. So what we are doing is that before we have a system, this was our Rn, and we have the vector field here in this surface. And now we are put in an extra coordinate. This is the lambda, and so we have Rn plus 1, and now here the vectors, since we are adding this one here, these vectors now have a component in the other direction, so they are no longer in the surface, but they are going out in here, say. So instead of this vector here, you have this vector here that have a one component in this direction. So you move now, your solution moves in time like this. So it moves up like this, but also in time. Moves like this. So we have the problem in R plus 1 dimensions, n plus 1 dimension, okay? But it's the same. So this way we generalize from autonomous systems to non-autonomous. So from the point of view of vector field, it's the same. There is no extra structure. To solve the system, it might be easy for this system in some cases, but for practical reasons, but for the theory, it's the same. So usually we stick with this autonomous system. So this system here, this system in general. So this here is our f hat of u hat. Okay, questions? So now we are going to look at the fixed points and stability. So we have this system, du. This is for autonomous system. For non-autonomous is a bit harder to study, but it's similar. We have our system. And we want to find solution of that. And suppose at some point u0, this is 0. So the solution is just a constant, ut equal to u0. So these are the easy solutions. You look at the f where a point where f vanishes, and this gives you a solution. So our points where our vector field vanishes. So the solution is like this. And when you have these solutions, you want to see how they behave in a neighborhood. I don't remember if I put it here. No. And so we have two definitions which are important for knowing what happens near a point. So suppose you have a point here where the solution is stable. So you have a definition here what if the solutions near these solutions, near the p equal to constant solution, are stable or not. And this definition is the following. Suppose you will say that this point is stable if given any neighborhood up, this is the big one here, there exists another neighborhood Bp such that for any point here, the solution does not leave this neighborhood. So if the solution here, I am using some other notation. If I have a gamma of t, which gamma of t0 is contained in Vp, then gamma of t is contained in Up. Notice that here you give the Up, you say for any Up, so this can be arbitrary, there exists a Vp, so once you give this, you find this other one, so such that if you start the solution here, the solution doesn't leave this region, okay? They not need to be equal. Okay, this is stability. I think I had the plots somewhere here. For instance, here are their examples. But let's discuss first this other definition. And we can say that it's asymptotically stable. This is a stronger condition. So a solution is asymptotically stable if it is stable first, so it has its same property, and also the solutions that you start in this neighborhood from Vp, so it's asymptotically stable if there is a neighborhood Vp such that if you start inside Vp, the solution when you take t going to infinity goes to p. So this is an attractor. So any solution you start here inside Vp goes in time to this one. So this is asymptotically stable. It's a stronger condition. Usually that means that there is some dissipation. So let me show you two examples. So the bacterial equation, the bacterial growth equation. So there is a term A is positive, A and B are positive. So you have this term here that says, okay, they reproduce, so there is a growth rate that is proportional to the number of bacteria, and then there is a term, a negative term that balance when there are too many bacteria, they don't have anything to eat, or they compete a lot with the food, so you have a term that limits the growth. And this system has two points, right? Two fixed points. One is x equal to 0, so this is a 0 of that, and the other is when x is equal to a over b. So these are two solutions, x of t equal to 0 and x of t equal to this other constant. This one, the 0 is unstable. Why I know that? Because if x is very small, this term wins, and this has an exponential growth. So if I am here and I do a small perturbation, this will grow exponentially, right? Then it will, when it gets near here, it will stop growing and will be like this. But here it will grow. So this point is not stable, right? Because if I cannot get a neighborhood here, any neighborhood, say, small enough, I have to take a smaller than this, right? But this is my u of p. Say this is the neighborhood, and it's clear that wherever I take any neighborhood here, when I do the evolution, I will go out. So this point is unstable. Now this point is stable because when I'm in this point, this is 0, and so I have the solution here, but when x gets a bit bigger, this term wins over this one, and so this becomes negative, so it drives the solution in this way. So the vector field here points like that, the vector here field here points like that, huh? And here points like that. So since the vector here points towards this point and this points this way, this will be stable. So any neighborhood I take here, it will go to 0, so this is asymptotically stable. It's not only stable, but also asymptotically stable. So this is stability, and we are going to see stability not only for ordinary differential equations, but for solution of partial differential equations, around solutions, stationary solution. What happens if the solution is not stationary? Do we have any let me see. Here I have this other example before I continue. This example is the t dx is equal to a to x, where a is a matrix. And you can ask yourself when this system is stable, and you discover that, of course, x equal to 0 is a solution, so you want to know whether this solution is stable. So if you perturb the solution nearby, it will move with the exponential, right? Xt, the general solution is the exponential. So this is a perturbation, doesn't matter because it's linear. And you can ask, okay, when this system is stable, and it's stable if the real part of the eigenvectors, eigenvalues of this matrix are less or equal to 0. Because if they have a real part negative, they will circle around, the solution will circle around to 0, so it's asymptotically stable. And if the real part is 0, you know that they do orbits. So this is a solution. I mean, this is the case when lambda I is different from lambda j for all. So the matrix is diagonal, so you can diagonalize it to lambda 1, lambda n, and so you treat each one of them separately. And you know that the solution will be e to the lambda 1 lambda it. So if the real part is negative, it goes like this, and if the real part is 0, it goes like that. And if the real part is positive, it is not stable, right? Like the first example we saw. If there are eigenvalues that are equal, then we can have this Jordan block, remember? So, for instance, the metric can have a form lambda 0, lambda 1, and in this case, we have a solution that grows with t, so this is unstable also. Right? So we know all these things. Remember, when you have a matrix like that, e to the it has a part which goes like e to the lambda t times a polynomial here, 1 plus this. So this t here is start growing if the real part of lambda is equal to 0. If the real part of lambda is less than 0, strict, then everything is stable. So many times we analyze stability doing perturbations, and so we reach to this problem. So when we get to this problem, when we linearize, we get this equation, and so you can analyze it completely. You look at the matrix A and you check whether the eigenvalues are different, whether the real parts are negative or not, etc. And you can have a very good panorama of what is going on. Here, in this case, the point is unstable because if I take whatever neighborhood I take here, the solution will go away in this direction and this direction, or in the negative direction will go away in this other direction. And these points are stable because if I take a neighborhood here, the solution will stay around there in a neighborhood like this. Okay? So this is stable. Okay, I thought I had something else here. In the notes, I had a theorem about the stabilities of general systems, but I thought I have here the theorem. We are not going to prove it, but I thought I have the statement of the theorem here, but no. There is a theorem that says given a system like this, F differentiable and F of I not equal to 0, then if you study the system, the perturbation, so this in coordinates is like this. These are the components. I take the derivative with respect to the position and delta y here. This is a linear system, so this is a matrix. So you look at the linearized system. We are going to come back to this later. Then you can show stability, system is stable. Around why not if real lambda I, the eigenvalues of this thing, have negative real part and it is not if some of the eigenvalues is bigger than 0 for some. Lambda j for some j. Notice that here we don't have the equal here because in the nonlinear case we cannot treat. We need more information to treat this. But at least you know if these eigenvalues are negative, have a real part, negative real part, then the system is stable. And if some of them is has a positive real part, you know it is unstable. So if you want to look at this theorem, it's in the notes, but we are not going to prove it. So now we are going to discuss the theorem, the fundamental theorem for ordinary differential equations. So this B here in the notation is what we call F, or F, the vector field. And we say that it's continuous differentiable in a neighborhood of some point M. So we have some neighborhood of some point, a neighborhood of this point, and we want to have this vector field here differential. Okay, then there are several things that this theorem will tell us, and so we have a number then with the I. And the first thing is that there exists a neighborhood of UP of P and an open set Y of R, such that given any point here, this is Q, and any point here, T0, there exists a differentiable curve gamma Q. So we have a curve here, gamma, satisfying that the derivative of gamma is the velocity of gamma is the vector v at every point gamma q, and at t equal to t0, gamma q goes through q. So we have it satisfies the equation and has a initial condition that goes through q at t naught. Okay? So notice that says there is a neighborhood, right? There is a interval, open set. We cannot say more than that because we have this example where the solution ceases to exist at finite time, so we know that y cannot be R, complete R. It has to be, but notice that it says, okay, there will be a UP, and this interval is the same for no matter where I take the point. Right? So I can take another Q prime here, and another curve here, etc. And they all have the same interval. So the existence interval is the same for all the points. Okay? So wherever I take the point here, at least I know that I have solution in this interval. It's the same for every point here. So there we have existence. And we are requiring this continuous differentiability because uniqueness. Remember that this example had many solutions around t equal to 0. So that's why we are requiring, here we are requiring more than needed. Actually, Lipschitz is enough, but we choose to put more. Doesn't matter really. So that's the first point. We have a whole, given any point, we have a whole neighborhood where every point we take, we have a solution that goes through those points. Then the second is about uniqueness. So we have this thing here, and we have a solution. This is the point Q, this is the point P, and this is UP. So we have a solution here that goes there, and another solution that goes here, gamma 1 of Q and gamma 2 of Q. And then the theorem asserts that they are equal in the intersection. So we have a gamma a one like this, and the other like that. And in this intersection, so from here to here, they are the same, right? So this is, we have uniqueness, that's why we needed the C1 or Lipschitz. Okay, so we have uniqueness. The way we express uniqueness is like that. The set is very important and says you have this, again, this point P, the neighborhood UP, and now you think of, you know that for every Q here, we have a solution going through this point. And we call it gamma Q of T. So you can think of this as a function of UP cross I, because I is the same for all points, right? So this is a function. I give the initial condition Q and the time T and give me a solution, right? So you can think of that as a function not only of T but of Q, okay? So Q here is a point in this neighborhood, and this is the existence interval. And the theorem says that this function is continuously differentiable in Q and T. So it's continuously differentiable in this. What does it say? That if I move a bit the curve that goes through here, it will be closer. So if we move, it will be very close. Okay? It's not the case that if you move a bit here, the curve does something totally different. It's not that they will go like this. I'm missing something here. Okay, I found it. So the fourth point is the following. Suppose I have a region U here, compact. So in the case if we are in Rn, we know that this is, in Rn is close and bounded. With the usual topology. So if we have a region of the space M, which is compact, and in this region B is defined in every point here. So B or F, whatever, B. So it's C1 in this region. and we get any point P here, then the curve that goes through this point, gamma of P, can be extended forward and backward to the boundary of U. This actually one second here. This, I think, here is a bit awkward phrase. This can be extended backward either to the boundary of U or infinitely, or remain inside. Indefinitely, for all times. This should be like this. What it means is either this curve just goes away in finite time, and the same here, up to the boundary, or it stays here, so you can do something like this. This is another possibility, okay? But they are the only possibilities. And how do you prove that? Well, we can take this as an exercise for topology, right? What we say is, okay, we know this theorem that says given any point x in this neighborhood, there will be a neighborhood of this point, UP, such that any curve in UP will, there will be a curve going through every point here, Q, such that we are going to be inside this neighborhood, and some finite interval U that I will put a Q here, a P here too, UP where the solution exists. So given this U here, I can collect all these UPs, right, and take and I know that these UPs are open and cover U, because I take every point here and I do my neighborhood and they cover all U, right? So for every point I have this, but I know that since U is compact, there will be a finite cover UP of I, so there will be some points here, I, J, 1, 2, 3, etc., that will cover this with a finite number, right? So I can take that cover, and that cover what it says. Suppose I can cover this line that I want to find. I can cover this region with some number of lines. So I will, suppose I start here, I come here, I go by this cover, I know that there is a solution that exists here, there is another solution exists here, etc. And this wire, I have the covers and I have the intervals. And these intervals are all finite. So you see, I can go along these covers, these members of the cover, and get up to the boundary, right? Because the solution exists up to the boundaries here, right? So I can continue whatever solution I get, I can extend and cover all this because compactness. So this proves this. Knowing the one, I can prove the fourth by just compactness. And here we have another corollary that is important. The one before was in some sense a corollary also. And this says, okay, suppose we have now a one parameter family of vector fields. So this F not only depend on U, but in some coordinate lambda, some other parameter. And this lambda is in some neighborhood A of R. Of course, we can take Rn, etc., but just one parameter is enough. And then we say, given any, let me change the notation here because let me change this to Y lambda. So we have the U where the vector field is defined, and we have a point P here, and we have a T0, so we have an interval here, T0, this is where the time is, and we have some other interval here of R, this is where the A is. This is A, this one here. So we have given the U, we have a solution. So at P we have a solution that goes from this interval to this interval to here. So given any parameter lambda we put and any time, we have a solution that goes through this point. And what this corollary says is that if we think of the solution of a solution with respect to the initial data, the time, and the parameter, then the solution is C1 with respect to all this. It's unique and is C1 with respect to all these dependence. So it depends differentiably on Q, that we know because it was part of the theorem. It depends on T, but also depends on lambda in a continuous way, differentiable and continuously differentiable way. And how do we know that? Well, suppose your system was like this. So now you extend your system, put lambda as a parameter also, and put the evolution is 0, so it's constant. So now you have this system. The solution of that system, it has this vector field that is 0, so lambda remains constant. And we apply the theorem to this whole system. And so since the system was continuously differentiable with respect to the initial position Q and T, since now Q is Y0, say, and lambda, then it's differentiable also with respect to lambda. Why is this important? Well, because suppose you want to perturb a solution. Suppose that this gamma naught here, say gamma naught was a stable solution we have before. I don't know why I cannot write here. Okay. Gamma naughts of t equal to some constant, gamma 0 say. So that's easy. So we can perturb a stationary solution with something and see the stability, trying to check the stability. So we do this perturbation, and then we have this one parameter family of solutions where we move a bit the initial data, and so we can take the derivative with respect to the parameter of the equation. This is the equation, where here we put the lambdas here. And so, and this we can do, right? This is just when you take this derivative and evaluate at lambda equal to 0. Since this is differentiable, I can put this derivative inside here. And so what I will get is that the derivative of this term with respect to time is equal to the derivative of the vector field with respect to the coordinates times the solution. So this is a linear system plus some derivative of Bj with respect to lambda. So how this vector field changes with lambda. And this is just a vector that doesn't depend on the solution. So this is all evaluated at, I cannot write over this thing. This is all evaluated here at gamma naught and lambda 0. And so this system is of this form, right? So what we have to do now is to use the theorem that I mentioned, that I have here is the theorem, finally I find it. That tells me when the system is stable. So I have, for looking at the stability of the initial system, which I don't have it already. The initial system was d gamma dt equals to b of gamma. And we have a gamma naught of t, gamma naught of t equal to gamma 0, a constant. Then this system is going to be stable if, when we look at this matrix here, which is just a derivative of b with respect to the parameter, then it's stable if the real parts of the eigenvalues of this matrix are negative, and it's asymptotically stable in this case also. No? And if any of the lambda has a positive real part, then it's unstable. So we have this general theorem. And for that, we have to do this pass, right? Go from here to the linearized system. And we can do that because we know from the theorem we have before that if we change with a parameter the equations or the initial data, then the solution changes in a smooth way so that we can take derivative here. So this is a Taylor expansion in the solution, which we are granted because of the theorem. Right? So we can play stability, etc. This basically is something that we can always do. We can do this only because of the theorem. I think we can let me give you these examples and then we stop for a while. We take a rest. So the first example is equation we saw first, the dt of x equals to ax minus bx squared. And so to see the stability of the stationary points, we have one at x equal to 0 and one at x equal to a over b. So for this x equal to 0, we just take a perturbation, which is delta x. And here the parameter is s. We were using lambda, and here I'm using s. I don't know why it changed. So the matrix you get, a times lambda, is you have to take the derivative of this equation when you change the parameter with an s, right? So here goes like this is the curve, the family of curves. I have to put delta x times s here and take the derivative. So it's the derivative of that. And I evaluate at s equal to 0, and that gives me this, right, the first term only, because this has an x. And so since a is positive, the real part of the eigenvalue, which is a, is positive, so this is unstable. For the second case, the curves we take are sigma delta x equal to the value at the stationary solution, which is different from 0, plus the perturbation. And so when we do the calculation, we know a times delta x should be the derivative of this thing now, but evaluated in these points, at s equal to 0. And what we get here is, when you do these derivatives, you get minus delta x. So this is stable because the real part is negative. Here I have the physical pendulum. It's the same, these are the equations. For the case of the origin, the solution which is stable, we know the theta equal to 0 and set this is the velocity equal to 0, is this point. And this other stationary point is this point here. One is here, the other is here. And so for one we take this perturbation, so a small perturbation, and obtain this matrix here. And from that you get, you compute the eigenvalues of that, and you find that there are two eigenvalues, and both of them have a negative real part, because this quantity is smaller than k. So you have two real parts. This, by the way, this is the pendulum with some dissipation here. And you can do the other exercise. Do this point. Okay, let's take a break. And now in the next one, we are going to use to prove Euler method, to prove the theorem using Euler's method. So let's get together at 11:45. Here we are going to make the proof using Euler's method. So first I have to explain Euler's method a bit geometrically, and then we do the proof. So now we want to prove the theorem, actually the first part, which is an important one. And I remind you what is. It says that if you have a system and then take any point, well, and F is Lipschitz in some region M, and then you take any point P belonging to M. There exists a neighborhood of this point P such that, so we have P here, UP, such that for any other point Q, there exists a neighborhood UP and an interval in the reals Y, such that given any other point Q on UP, there exists a solution going through Q and having as interval of the definition the Y interval. Okay? That's a set. So we want to prove that. And for that, traditionally this is proven using a method of a map that is contractive. We are not going to do that because we want to use some method closer to the method that one really uses to solve equations, and namely Euler's method. So remember we have, let's draw it here. So we have here a vector field F defined everywhere, and so we can use, and we are looking for curves that go through this point, say this curve. The vector field here goes like this, and then goes like this. And so one way of solving for it is to approximate. You take any point here, look at the vector, let's say here the vector points in this direction. So you go along this vector a bit with a straight line and go to that point. Then at this point you look at the vector, and the vector field, say, is pointing in this direction. So now you go from this point a bit on this, right? So this will be, suppose this point was a 1, so this is the vector f at x1, and you go quantity delta t, and then from there you reach to this point x2. This is x1 plus this, right? When you reach this point, you go from x2 to x3, so you add another point. So you have x1 plus delta t fx1, which is x2, and then you put here another delta t f of x2, and so you go to will be the point x3. So you go marching there like that, right? So you make an approximation by straight lines. So you make a function like this, straight line. And when you take delta t smaller and smaller, you will be approaching this, the exact solution that is this green one here. So when you continue, of course you will be going away, right, for any finite delta t, but in the limit you should come. So if you take a smaller step, half of the step, you will go closer with many more lines, and you will get closer. So we want to use that. So the setting we are going to use is that these functions that we do, the red function, say, I don't remember how it called it. I think this is h of t. I'll give you all these functions are going to be all in the space of bounded continuous functions in the interval, in some interval. So this interval is 0t. We are going to use. So these functions are here, and so we know that we proved before that this space is complete. Remember, this was one of the things we proved. So that if we can show that this sequence, when we take delta t smaller and smaller, is Cauchy, then we know that there will be a limiting solution. So this xht, when h goes to 0, will converge to some element in this space. So this is what we want to do. So now we have to fill out all the details, but basically is this. So to clarify the notation, we want to solve this system. I'm using x instead of y. And here we have the theorem. So we assume some point and a radius r. So we have a point xc and a radius around this point of radius r. So these are all points such that x minus xc is less than r. Right. So this in any norm, right? No problem. So we have this thing here. So we take r such that in a bigger ball of radius 2r, this radius is 2r. Such that now we take another point here inside this ball, x0, and we are build a solution that goes through x0 when t is equal to 0. So the solution we are going to want to prove the existence, right, is a solution that goes to this point. This is any point in this small region. So this will be the UP that we have in the theorem, in the other version of the theorem. Right, so it's u of xc this is a UP, a US of X, and there will be an interval which is common to all. So we are assuming that in this bigger region, F is defined. All of the here is defined and is Lipschitz in this bigger ball. And so what we want to prove now is that given any point x naught inside the smaller ball, there exists a finite time interval, 0t, for which there is a unique solution for this system and satisfies that x naught is x of t equal to 0 is equal to x naught. So now let's get all the intervals analysis. So first let f be the maximum in the bigger norm, in the bigger region of the vector field. So we look at the maximum in the norm of the value of this vector field. Here if we are in here actually should be a norm here, any norm that we are using in the vector field. And we fix a t, right? And the t we want to be smaller than r over f. What does it mean this, right? If you take f times r is the longest distance the solution can travel, because f is the biggest velocity and this is a time, so f times t will give me the longest region where the solution can go, right? So this we want to be smaller than the radius r. So we want to make sure that the solution doesn't exit the big region, right? If we start here at some point and we evolve the solution during this time, we are sure that we are not going to reach the 2r. So that's the condition. And another constant we want is the Lipschitz constant. So the Lipschitz constant is the constant bounding the differences in all this ball. So since we are assuming that the f is Lipschitz, we know that there exists also here there should be norms. That the difference between the values of the vector at 2 points is less than some constant times this, right? So we have this other number to play with. So now we divide the integration interval 0t into r0 steps. So we cover this interval with so this is a 0, this is a 1, this is 2, etc. And the distance between these two is h0, which is t over r0. And so these times, this is t1, t2, etc. ti. So this distance is h. And compute the finite sequence of points using Euler's approximation, right? So this point is where you were first times h times the value of the vector field. So you are doing this. You start here at x0 and then you go along the vector field. Right? So if this is a vector field, you move some delta h, which usually is smaller, and this way, okay? So you are doing this. So this is a set of points, and with this set of points, you interpolate them in a linear fashion, and you get a function. This is a function now in the continuum, and it's a function that is defined in every step like the continuous function, okay? So you have 4 points now, and we are now doing this, connecting these points with straight lines. So this is the function. So this is the approximation. It's a continuous function here. And it's bounded, right? So it's an element, this thing here is an element of C0t, of bounded continuous functions. By construction, everything is bounded and it's continuous. And now we repeat this construction, but with more points. We take n naught times 2 to the I and call this number of points ni, and correspondingly take hi to be smaller, to be h times 2 to the I, to the minus I. So we are getting smaller and smaller spaces, and so we get a sequence. How did I call it? Well, a sequence in H, so I have a XHI sequence of solutions in this space, of approximations in this space. And what I want to know, since this space is complete, the only need now to prove that this is a Cauchy sequence. Because if I can prove that, then I know that this has a limit sequence, a limit function, a limit element of C. Notice that when I get to here, I will only know that this function is continuous. I will not know that it's differentiable. So then I have to show to you that this function is also differentiable, so that to be a real solution of my problem. So now I have to show that these sequences converge. So we look at the sequences. So we will look at the sequence with I, two continuous sequences, I plus 1. And we want to see that these sequences, the different go to 0 with I. And then we have to show that they go to 0 with all but this is easy. And so we have now one sequence, the I is like this, between 2 points, and the other one, this one, has something like that, right? This is one of the segments of this thing here, one of these. And the other is this one. And I want to compare the distance between this one and this one. And I want to see whether this distance goes to 0 or not. So we have the x at nh, this is n. We have h, from the other sequence, we have this point is the point m plus 1/2 tan h times h, and I I have a mistake here. There is a 1 here. So these are the 3 points. NH, this is n plus 1/2 times h, and this is a point n plus 1 h, and this is n plus 1 in the other. Right, so we have to compare these two. So this is a very long calculation, but okay. I'm missing something here. I'm missing the first line of this. So this is the distance between the middle point on this one, that will be, you see, is n plus 1/2 h, and this one, this is in the smaller sequence in the same place, right? It's the same at the same time. So this will be like this. Let me draw this. This is the difference between, we have this interval and this interval in the other sequence, and it's the distance between this point, we use another column, this point here and this point here, this distance. So we write these ones using Euler's method, you see here, and we will subtract this thing also in the other sequence. Yeah. So here I have x over 2 times. Here we have everything is in h. So this is because we are marching only half. So that's why they have here. And here we are evaluating in this thing, because we are taking the whole step. So we are comparing this step with this step. And so we rearrange things here, and we take this minus this, and then the terms which have h, like that, right? And then we use the triangular inequality to get this in here plus this in here with h over 2. And here we have f into these 2 points. So here we use the Lipschitz condition to say that this is less than the interval between this and this. So we get L1 from here plus HL over 2, right, from this times L, and the same interval here. So this is the relation that, so between these 2 points. And then I have to compare these two, because I don't know whether the distance, smaller distance, is this or this one. So for the endpoint, this distance, I'm writing everything in terms of this distance, right? This is sort of given, and I look at this one and this one, and I'm bounding this one by this factor times this, and now I have to bound this one by some factor times this distance. So this is a bit longer, because here I have to do 2 steps, and these are the steps. So you go first to the middle point, and then you go to this, and this other, well, is a long calculation, but not difficult really. Then you use again the Lipschitz condition here, and what you get is this condition here. So we have this factor times the difference. Remember, this difference is this one here. And then we have this other factor that comes from here, right? Here you have the f only, but you have h squared over 4 times the Lipschitz condition times the maximum of this f. So we can bound this maximum by just the sum of these things. So you get this thing here. Well, not the sum, really. This is the same factor that we have here. So we are adding this one. So this is the maximum. So we can bound the distance between this one and this one in the whole interval. So we are maximum bounding the distance between this and this by this relation. So you have the maximum here is with respect to this distance plus something that goes like h squared, okay? So if we now look at the maximum distance, right? If now suppose you are having this, we start from the same point, and now we have another one which goes, these are the points. This one goes like that, say. So we want to bound this distance, no? The final distance. So for that, and since we are bounding any distance here between the two, so we just sum up these bounds over the whole region, and we notice that here we have this term. This is a constant, and we have this term to the j. So it's a geometrical sum, so we can get the solution of this geometrical sum is this times this constant, and we can rearrange these things a bit, and then we can bound by e to the t to the l minus 1 times h f2, okay? So the distance goes to 0 like h, because these are constant. So this goes to 0 like h. And h, remember, goes to 0 like 2 to the I to the h naught. Huh? So the sequence is Cauchy, okay? You might say, well, you have the sequence, you only prove that hi minus xhi divided by 2 this sequence is Cauchy. Can you prove something if I and j are different but bigger than some number? And yes, and you can do that, and at the end of this note there is a way of proving it. But this is enough. It's clear that if two consecutive terms go to 0, then when you go further and further, still go to 0. So we have a Cauchy sequence, and this Cauchy sequence goes to this function. There is something that I haven't proved yet for you, but maybe you will discover, otherwise I will prove it. You will ask me the question and then I will prove it, or I will show you. So we have this x of t belongs to c of 0t. So it's a function which is only continuous. So now you write the equation, you integrate the equation, right? You have the xt, so you integrate the equation. Remember, the equation was dx dt equals to f of x. So you integrate, here you get that x of t is the initial value plus the integral between 0 and t of this thing. But this function here is continuous, and this function is even better, is Lipschitz. So when I integrate this, I get a continuous function, right? But so I have this is okay in the space, right? But notice I have x here and x here. So if I differentiate, I will get the f of x, and so I know that this function is also differentiable, right? So in fact, from this integral form, I know, taking a derivative, that x of t, xt is differentiable. In fact, you can see that you can have any t here in the interval, and we can do the Euler's method. Just tell us that this value here at the point nh, say fixed, is equal to the initial value plus all the Euler's terms, all the sums, right? And this, when you go to the limit, where h goes to 0, this converges to the Riemann integral, right? So this way you get this formula, that is its value. So that's what I was saying, that this function is continuous, so I can take the limit. So this way you get an xt, which is a proper solution. And x of t naught, or at t0 in this case, is x of c, x of x naught, and x naught was inside this ball. So we have the ball, this ball of radius r was our up of x, where p is xc, and we have a solution in an interval that was 0t, where t was the radius divided by the maximum value of the vector field. So we have the t and we have the up. So that finished the proof, and the thing I wanted to mention is that I cheated a bit, because what I say is, if I have this line here and this line here, that the maximum of the difference between these two lines is either here or here. Right? You see this and you say, okay, it's true, but we have to check, right? Because in particular we are using any norm. So how do we prove this? So in fact what we need to prove is either this, we just take in green, just prove either this is the maximum distance or this is. So we have two straight lines and we want to see that the maximum distance between the straight lines is on the extremes. So we consider these two lines. the one, say this point is x1, this point is x2. Consider this line, and this one you call x1 prime, x2 prime, and consider these two lines. These are the lines which are here. So now we look at the distance between them for the same t, right? We look at the same t. So we move here. We are looking at distances here with the same t. Not arbitrary distance, but at the same t. That's what we need in the proof. So we have this distance. We put one of the function here, the other here, and we rewrite this, and this is the distance between these 2 points times t, and the distance and this, the line that goes from this difference to this difference. And so this is the line. So you can see this is the line. So you have, so this is the origin. This difference is this line here. And when you move around t, you go from this one to some other one. You move like this, right? Because you are moving from this point to this point, so you go like that. So this is x1 minus x1 prime, and this is x2 minus x2 prime. So we are looking at this vector and this distance when you move here. So we are looking at the distance between this point and this. Let's make it another color. So this vector here is this vector here. So we are moving like that, and we are looking at the distance to the origin. Let's use another color. So the distance to the origin is this here, at this point. So we want to see that we obtain the maximum here or here, which is, and so how do we do with the things we know about norms? Remember that a norm was something which has some level set that has this property that if this point was here, the opposite point was here. It covers it surrounds the origin. So if I go in some direction, I always cross. When I cross the other point, the negative point, it is there, and it's convex, right? So now we are watching in this. So this is any norm, and we are looking at this vector here, right? So we want to see the distance between these 2 points of any point here to the origin. And you see, since this is convex, if I bring this norm, rescale this norm, I can make it smaller, and this norm will touch, this surface will touch it, either here, or will be the whole thing, right? And all these points are going to be inside. Why is that? Because it's convex. So if this point is inside and this point is in touches, then the whole segment has to be inside. So this tells me, but whatever norm I take, because convexity, the points, the extremal points are the ones that will give me the maximum, one or the other. Okay. So this way you are sure that the maximum is is found here, either at this point or at the corresponding here that I miss. So the maximum is either here or here. And this it's more or less intuitive that is like this, but it's nice that you can show with the things we know about norms, you can do this drawing and convince yourself that it's okay. Okay, with this I'm going to finish now. So tomorrow we are going to start doing all the numerics of ordinary differential equations. That will take us another day, maybe a bit more, we'll see. But probably we'll be finishing ordinary differential equations before Friday, before Thursday, probably Wednesday or even Tuesday. So there will be time during the mornings and tomorrow we are going to give you the first lab that you have to bring, and we'll discuss the homeworks and also give you the homeworks for these things. So tomorrow at some point we can start looking at the first lab and the homeworks if you have questions, and dedicate say 1 hour tomorrow and 1 hour or more on Wednesday to discuss the labs and the homeworks. Okay. So now we are more we cover all the mathematics, almost all the mathematics we need, and so now we can go to play around with the equations. First ordinary differential equations, then we are going to be hyperbolic equations, how to do it analytically, numerically, and so on, and then elliptic and so on. So I'll stop now and we'll continue tomorrow. Are there questions? No questions on the other side? No? Okay. Then we continue tomorrow morning with the numerical part.